All right. Last time we ended up talking about how the first derivative what the first derivative is used for. Let's look at everything. So what is the original function used for? What information can we get from the original function? No. Remember, we're looking at polynomials now, so that won't do us any good. What is the original? What can we do with the original equation? The degree of the polynomial.
The rate of change?
Not from the original function. That's the first derivative. But yeah, what you're thinking about is if we put in the equation, the slope equation, we can find it. But that's not from this equation. Just from the original equation itself, we can get the degree of the polynomial. What good is that going to tell us? It's the maximum number of solutions possible. But yes, you're right about that also. Not the number of turns, though. Since the degree is the letter n, we have ax to the power n. That's the degree. N minus 1 the number of vertices. For example, we have y equals x squared. Y equals x cubed. These are, of course, exaggerated. Since n equals 2, 2 minus 1 equals 1. We have one vertex. N equals 3. 3 minus 1 equals 2. We have two vertices. Actually the maximum number. Maximum. It's the maximum number. Maximum number. It's the maximum number of vertices, n minus 1. The leading term tells us the end behavior. End behavior is a shape and direction of the graph. So the leading term is ax to the power n. So if the degree is odd or even, and if A is positive or negative. So if A is positive and N, the degree is odd, the end behavior looks like this. One side goes down, the other side goes up. If the degree is odd and it's negative, then one side, the left side goes up, the right side goes down. If A is positive and is even, both sides go up. And if A is negative, both sides go down. So we know what the shape's going to look like. We know the direction of the graph. We know the y-intercept. And we know the points of or on the graph. So all that comes from our original function. The first derivative tells us what?
That's the rate of change.
That's the rate of change. Slope or the rate of change. At any point on the function. What else does it tell us? What else is it used for? And it happens, it relates back to the rate of change part. So what can we do with it? You set it equal to 0.
Did you mean the instantaneous, or is that the same thing?
It's the same thing. Because if it happens at one point, then it's instantaneous, not over a few points going down. So if we set it equal to 0, we find the vertices. Which are the max, min. It also tells us where the graph of the function is increasing and decreasing. So how do we know if it's increasing? Because remember, we're dealing with the slope. How is the slope? How do we know if the function is increasing? By looking at the slope. Positive or negative, yeah. So if the first derivative is positive, it's increasing. If the first derivative at some point x is negative, it's decreasing.
What do you think? Tells us where the graph of the original function is increasing? Or where the
Well, the derivative is a slope. What is increasing? The function's increasing, the points of the graph are increasing. It just tells us if it's increasing or decreasing. Is the graph and this interval is increasing or decreasing? So here it's positive. Here it's negative. And here it's positive again. So it's increasing in those intervals. And in this case, it's decreasing in those intervals and that interval. It's always, we look only at the points of the domain of where it's increasing, decreasing. And we cannot use the endpoint, so it's always a parenthesis. So that's what we're doing so far. Oop, we didn't finish. I forgot another thing up on top. The original function. It's also good to find the x-intercepts. Set the function equal to 0. All right. So that's up until the first derivative. So now the second derivative tells us about the concavity of our function. Concavity, it basically, it's the bending of the curve. Okay, we have two examples here. I'm exaggerating there, but this is what it's talking about. If the curve opens up, this is the concavity. This is concave up, because it opens up. And that's concave down. Concavity deals with the second derivative. If f of x is positive, then that interval is concave up. Excuse me. If the second derivative is 0 for those values of x, then that interval is concave down. Okay, now here I talked about an interval. What interval am I talking about? By interval, I mean the domain of x on both sides of the point of inflection. The point of inflection is where the graph of the function changes concavity. Because this part of the graph is concave down, this part of the graph is concave up. So there has to be a point x where the graph is neither concave up nor concave down. So if it's neither concave up, when is it concave up? When is it concave down? It's concave up when it's positive. It's concave down when the second derivative is negative. So the point of inflection occurs when the second derivative is equal to 0. That x is the point of inflection. So, all right. So let's look at some examples. Example 1. Find the intervals where the following have concavity. I'm going to add an extra one to this one. Find the intervals where they have concavity. How do we do that? Find the intervals of concavity. What do you think the first step is? The first derivative, find the derivative. What's that going to tell us? We just went through the whole stuff in the notes. No, we're going to find the second derivative. Let's see what happens here. So step 1. The first derivative of this first one is what?
1,
And then the second derivative is
0.
0. So we know that this one doesn't have a concavity. We know it. Why? Because the first derivative is a constant. If the slope is a constant, what does it look like? Oh, they're all like, yeah. What kind of line? Horizontal. There's no change in altitude. So because it's horizontal, there is no concavity, no bends. How about the second one? So it's 2x. And the second derivative is 2. So since the second derivative is a constant, what does that mean? Is 2 greater than or less than 0? So therefore, everywhere it is concave up, because the second derivative is greater than 0. Always. And we can also tell that we're going to have concavity because the first derivative can change from positive to negative and can equal 0. If you have a vertex, then you have concavity. So we can set this one equal to 0. Now we have a vertex at 0. That means it's either going up everywhere, or it's going down everywhere. Like that. It's either concave up, concave down. Because we have a 0 point. Let's look at the last one. Remember, the slope, the degree tells us the number of vertices. We can have at most 2 vertices over here. Well, it's a cubic function, so that makes sense. The exaggerated cubic function looks like this. We have n minus 1 number of vertices. The second derivative equals 6x. It's got a variable x. That means it changes. That means it can change from positive to negative. What do we do? Set the second derivative equal to 0. And solve for x. So we set this is step 2. Set that equal to 0. X equals 0. That x value is the point of inflection, which I'm simply going to call POI from now on. Since we have a point of inflection, that means on one side it's going to be concave up or concave down, and the other side it's going to be concave up, concave down. Usually is the opposite. Choose x values on both sides of the POI. And plug them into the second derivative. Well, let's if the value is positive, then f of x, the function is concave up on that side. If the second derivative is negative, the function is concave down on that side. Okay, so find the intervals where the following has concavity. So this one has no, so it has concavity everywhere, and it's concave up. What about the next one? What about 3 or C? Where, since it has a point of inflection, this is my POI. What happens to the left? Let's put -1 inside there. Six times -1 is -6. That's less than 0. So it's concave down. So to the left of 0, it's concave down. Take a number to the right of 0, a +1. 6 times 1 equals 6, and that's greater than 0, so it's concave up on that side. So what this graph really looks like is like this. The actual point of inflection occurs where? 0 what? 0 at the origin. Because once I found the point of inflection, I plug it back to the original equation, then I get the POI occurs at 0, 0. So to the left of it, I know everything is concave down. So this is curved this way at -1. At +1, I know it's concave up. So that's what the graph looks like. All right. Let's look at example 2. Now let's get some real looking equations. Example 2. Determine the concavity of y equals 3 plus sine x on the domain 2 pi. So what we do? Find the second derivative. So y equals 3 plus sine x. The first derivative is what? That's 0 plus cosine x, which is equal to cosine x. Very good. And then the second derivative. Very good. negative sine x. So what does this graph look like with this function? It's a sine function. There's the x, and it's raised up 3 spaces. So my origin shifts from here to here. Pi over 2, pi, 3 pi over 2, and 2 pi. So at 0, it's 0, plus 3 is 3. Pi over 2 is 1, plus 3 is 4. Pi is 0, 0 plus 3 is 3. Then negative 1, and then at 0. So this is what the graph looks like. We know we're going to have 2 concavities in there. Because where is cosine equal to 0? Remember, we have 2 vertices. Cosine is equal to 0 at pi over 2 and 2 pi. No, pi over 2 and 3 pi over 2. Cosine is 0 when we have the vertices. Since we know that that's a vertex, what do we know about this side, this interval? So from 0 to pi over 2, what's happening? Is it concave up, concave down? Concave down. Very good. Then we have from pi over 2 to pi, what's happening there? Concave down. Well, what do we forget to do? We just found the first derivative, set those equal to 0 to find the vertices. Take the second derivative, set that equal to 0. Where is sine equal to 0? At 0, pi, and 2 pi. So this function equals 0 at 0, pi, and 2 pi. The x-intercepts. But we can't use the endpoints because they can't be points of inflection. The point of inflection is the middle. This is concave down. This is concave up. So we know that from 0 to pi, it's concave down. And then from pi to 2 pi, it's concave up. So far, so good? Example 3. determine the concavity and the point of inflection of f of x equals x cubed minus 3x squared plus 2. So how many vertices are we going to have? Remember, always take away one from the degree. So we're going to have 2 vertices. Since we have 2 vertices, that means that they have to be different concavities, or the chances are that we get different concavities. So the first thing we got to do is find the derivatives. The first derivative is what? The derivative of x cubed is 3x squared minus 6x. 2 disappears. So our vertices are going to be where? Since we know we're going to have 2 of them. The vertices, set this equal to 0. Solve for x. So we have 3x equals 0, x minus 2 equals 0. So my vertices are at 0 and 2. Remember when I said, well, and then the next step, we have to find the second derivative, which is going to be 6x minus 6. That's the point of inflection. So set that equal to 0. We can factor out a 6. So x equals 1. That's my point of inflection. So if the x of the point of inflection is at 1, what's the y value? What's the location of this point? If the point of inflection is at 1, where is that on the graph? That's an x value. Plug it into the original. Remember, the original function finds us locations on the graph when x is 1. So we have 1 cubed is 1, minus 3 is negative 2 plus 2 is 0. So there's my point of inflection. Remember, I said from the point of inflection, pick a point on both sides of it. Well, we did that. We use x equals 2 and 0. When x equals 0, y equals 2. It's the y-intercept. When x equals 2, so we have 0 cubed minus 3 times 0 squared plus 2 equals 2. When x is negative, when x is positive 2, we get 2 cubed minus 3 times 2 squared plus 2. 8 minus 3 times 4 plus 2. 8 minus 12 plus 2. So 10 minus 12 is negative 2. So there's my other vertex. We know that this is a cubic function. It's an increasing function. So that means this graph has to look like this. The POI is at 1, 0. It is concave up. Where is it concave up? Where is it concave down? No. Where is it going? Negative infinity. This is down. Negative infinity to where? To 1. Very good. So this all, everything here is down. And then up. Very good. Everything here is concave up. Very good. Let's look at the next example. Example 4. Find the point of inflection of f of x equals x to the 5/3. So what do we got to do? We first have to find the first derivative. So what's the first derivative going to be? The power comes down, which is 5/3. And you subtract 1. So 5/3 minus 3/3 is 2/3. That's the first derivative. Then we got to find the second derivative. We have 5/3 in front. Bring the power down. And subtract 1. So 2/3 minus 3/3 is negative 1/3. Times the derivative of x, which is 1. Times 1. Because that's the derivative of the x. Which gives us 10 over 9. X to the power 1/3. So what do you think about this one? What's the point of inflection? How do you find the point of inflection? Set it equal to 0. Solve for X. What do you get? The only way a fraction can equal 0 and equals 0 is if the top is equal to 0. Since 0 does not equal 10, there is no point of inflection. Find the POI of f of x equals x to the 4th. So the first thing we gotta do is take the first derivative, which is what?
Works.
Then the second derivative. Very good. Then set that equal to 0. Divide by 12. So 0 equals x squared. X equals 0. So what's our answer going to be? What's that going to tell us? Do we have a point of inflection or do we have concavity? This is the x value in which our second derivative equals 0. So the point of inflection, if x is 0, go back up here. Very cautious guess there.
A little bit.
No, just take the first and second derivatives, take the second derivative, set equal to 0. And that tells us the x. If you get an x value, if it's valid, then that's the x component of the point of inflection. It happens at that x value. The point of it is plug it in the original, so it's point there. Sample 6. What are the point of inflections of y equals x to the 1/3? Although if I was to give you this on a test, I would have given it to you like this. So you'd have to take this and convert it to an exponential number. And there's the exponential conversion from radical to exponential. So the first derivative is what? Take the power, bring it down, so it's 1/3. 1/3 minus 1 is the same thing as saying 1/3 minus 3/3, which equals -2/3. The second derivative, bring the power down, so we have 1/3 times -2/3. -2/3 minus 1 is -2/3 minus 3/3, makes it -5/3. So it's -2/9, x to the power -5/3, which looks like so where do the point of inflections occur? What did we just talk about? If was it, yep, no point of inflection. Because you can't make the top equal 0. Very good. Very good. Example 7. A particle moving along a horizontal coordinate line with position function equals 2t cubed minus 14t squared plus 22t minus 5 for all t greater than equal to 0. Find v of t and a of t. And describe the motion. What will they do? What's the first step? Nope. Was this, we got first and find v. What is v? V is the first derivative of the position function, which becomes, carry the 3 down, 3 times 2 is 6t squared 2 times 14 is 28t plus 22t. And then we got to find the acceleration, which is the first derivative of the velocity, which is the second derivative of the position function. 12t minus 28. So what do we talk about? What do we know here? Describe the motion. Are there any vertices? Where? We get vertices where the first derivative equals 0. And first derivative is the velocity. Set that equal to 0. We can factor out a 2. We'll factor it out. So we got 3t, 3t. Second sign's a plus, which means they're both the same sign. They're both going to be the first sign, which is both minus. Three times 11 is 33. So what two numbers multiply to give me 33? When I add them, I get 14. 11 plus 3, 11 times 3. So our velocity function since nothing factors out of the first one, it's 3t minus 11. I can take out a 3 on the second one, so I just got a t minus 1. I can factor out a 3 there. So where are our vertices? So t is equal to 11 over 3, and t is equal to 1. These are my two vertices. since these are my two vertices, I know I have to have a point of inflection between them. Can we well, let's do that one first. Let's find the point of inflection. That's the acceleration, which is the second derivative of our position function, which is 12t minus 28. Set that equal to 0 and solve for t. So t 28 over 12, 14 over 6, 7 over 3. So the point of inflection at t equals 7 over 3 at the point s of 7 over 3 to 7 over 3 cubed, 14, 7 over 3 squared, plus 22, 7 over 3, minus 5. That's why I'm gonna stick with the answer. It happens at that point. Let's 8 now. Second derivative test for local extrema. So let's look at theorem 5. For local extrema. Suppose that the second derivative of the function is continuous on AB containing C. Why is it important if the second derivative is continuous on AB? Why is that important? What does that tell us? Well, if the second derivative is continuous, what does it tell us about the first derivative? It's also continuous. The derivative of a continuous function is continuous. And if this first derivative is continuous, that means f of x is continuous. That means it's differentiable on every point in the domain. So that means everything between A and B is differentiable. That means it's differentiable at a point C inside there. if the first derivative at C is equal to 0, and the second derivative at C is less than 0, what does that tell us? Is it a maximum or minimum? Remember, if the first derivative equals 0 tells us what? It's a vertex, horizontal slope. And if the second derivative, concavity, is negative, if it's negative, do we have a maximum or minima? Maximum. Then local max at that point C. If the first derivative at C is equal to 0, and the second derivative at C is positive, so we have a vertex. Second derivative is greater than 0, so it's positive, so it's opened up. That means we have a local min at C. And lastly, if the first derivative at C equals 0, and the second derivative at C is equal to 0, the test fails. We don't know what happens yet. Because we know there's a point of inflection. This is a vertex. This is a point of inflection. We don't know what else happens. So that's the theorem 5. It's the stuff we've been doing all along. Sketch f of x equals x to the 4th minus 4x cubed plus 10. Using the steps. Where are the extrema? Tell where it's increasing and or decreasing. Find where concave up and concave down. Sketch the general shape. Plot points. Okay. So what do we know about this function so far? By looking at it, what can you tell me? Okay. At most 3 vertices, what else? At most 4x intercepts. What else? Where's the y-intercept? It's actually 0, 10. But you're, yeah, it's a 10, it's y%. So where are the extrema? How do we find extrema? It's first derivative. Whenever you see the word extrema, max min, it's first derivative. So we got to find the first derivative of this function. So we have 4x cubed minus 12x squared. Set it equal to 0. We can take out 4x squared, leaving x minus 3. So they occur at 4x squared equals 0, x minus 3 equals 0. So the vertices, extrema happen there. Their points are f of 0, which is 0 to the 4th, minus 4 times 0 to the 3rd, plus 10. So f at 0 is 10. And f at 3 is 81. 4 times 27 plus 10. 81 minus 8, 108 plus 10. So 91 minus 108 is 17. So we have a point at 0, 10 and at 3, 17. So where is it increasing, decreasing? So let's find the concavity. The next one is find concavity. We're looking for the point of inflection, which is the second derivative set equal to 0. So it's 12x squared minus 24x. Set that equal to 0. We can take out a 12x. So x is equal to 0. And x is equal to 2. These are the points of inflection. Their locations are f at 0, which is 10, f at 2, 2 to the 4th minus 4, 2 to the 3rd plus 10. 16, 4 times 8. 26 minus 32 is -6. So 0, 10, add 2, -6.
So it's taking values and putting it back in the original function.
To find the points of the graph, yeah, we have to use f of x. And all of the first derivative and second derivative tells us the x values of where those occur. So we have a vertex at 0, 10. At 3, 17, we have another vertex. A point of inflection at 0, 10. And at 2, -6. What's the graph going to look like? It's a fourth order equation. A is positive. So both ends have to point the same direction. They both point up. In other words, a fourth order equation looks something like this. That's 4x cubed minus 12 squared. So that's a vertex. And that's a vertex. No, that's a point of inflection. This is a POI. Okay. We know it has to look like this since it's a positive A and its degree is 4. The y-intercept is that, but it's also it's a point of inflection and it's a vertex. Which means So the vertices are at 0 and 3. At 0, it should, nothing happens at the intercept. It's the first. Try it. Yeah. Yay. Mine's just the really short picture of it. That was a pretty ugly one. Now let's move on to an easier one. Example 9. Sketch the graph x plus 1 squared, 1 plus x squared. Okay. All right, so the y-intercept here is 1. Because if we set x equal to 0, we get 1 over 1. The x-intercept equals -1. Because that's the only thing that makes the top equal 0. So now we've got to find the first derivative. We have x plus 1 squared, 1 plus x squared makes it 2x. 2x plus 1 times 1. So we have 1 plus x squared, 2x plus 1 minus 2x, x plus 1 squared. Then combine those, we have x plus 1 plus x cubed plus x squared minus 2x, x squared plus 2x plus 1 plus x squared squared. X cubed, x squared, x plus 1. Two x cubed plus 2x squared plus 2x plus 2 minus 2x cubed squared. Just makes it cubed Four x squared minus 2x. Two x cubed, 2x. Uh-oh. This one has to disappear. One plus x squared, 2x plus 1 minus 2x x 1 x cubed x squared 2x x squared plus 2x plus 1 2x cubed 2x squared 2x and 2 2x squared cubed or x squared minus 2x. Two x squared, so those two disappear. So we have minus 2x squared plus 2. I got negative 2, so it's x squared minus 1. So set that equal to 0. So the only place that x squared minus 1 is x plus 1, x minus 1. So x equals 1 and negative 1. Those are my vertices. And then I need the second derivative. But hopefully by now, I mean, you should be able to do this. This is finding the first derivative. X squared. So we have f, g, f prime, g prime. So second derivative, negative 2x squared minus 1, negative 2x, it's x squared squared, 1 plus x squared times 2x, 2x plus x squared. Makes it 4x negative 4x 1 plus x squared minus negative 2x squared minus 1 4x 1 plus x squared. And this is squared, so it's to the fourth power. Negative 4x, 1 plus x squared squared. Negative and negative becomes a positive. 2 times 4x is 8x. X squared minus 1, 1 plus x squared. Okay, we can factor out a 1 plus x squared. And a negative 4x out. So that'll leave us 1 plus x squared minus 2 x squared minus 1. So that cancels with that. Negative 4x, 1 plus x squared minus 2x squared plus 2. X squared minus 2x squared is minus x squared plus 3. Let's leave it at that. So it's negative 4x, 3 minus x squared. So the point of inflection occurs at where negative 4x is equal to 0 and where 3 minus x squared equals 0. So it happens when x equals 0. So 3 equals x squared. X equals plus or minus cube root of 3. So those are the points of inflection. Wow. Sorry I went so fast. I mean, there's still a couple more problems I want to do, which we don't have time because they're all more complex. So what is it? What do we know so far then? In this one, we know that f of x is equal to this function. The first derivative vertices at 1 and negative 1. Point of inflections at 0 plus or minus radical 3. So we know the x-intercepts is at -1. The y-intercept is at 1. The vertical asymptote doesn't exist. Horizontal asymptote is 1. The vertex at -1 and 1. Point of inflection at 0 plus or minus radical 3. All right, let's see what all this stuff tells us. So we have a horizontal asymptote there. The y-intercept is at 1. The x-intercept is at -1. The vertex is at -1. So there's a vertex at -1, 0. So that's the point of inflections. 0, negative radical 3, radical 3. Zero is 1. So that's a point of inflection that has to look like that. The vertex is at -1. Oh. 1, 2 is a vertex. That's what it looks like. This is going to be an ugly one. Where is equals x plus 1 squared divided by 1 plus x squared. Yeah, that's right. which is what I agree. But it has to eventually go to that horizontal asymptote. Wow. These are all pretty ugly. What was I thinking? Want to do another one or? I'll show what the next one looks like.
Like, sure.
So the x-intercepts. So the top equals 0. Doesn't exist. There are no x-intercepts. Because x can never make this on top 0. So the y-intercept doesn't exist. If we set x equal to 0, it's a 0 on the bottom. So we have a horizontal and vertical asymptote there. I had a vertical asymptote at 0. And there is no horizontal asymptote because there's more on top. But we have a slant asymptote. To x. So you have a slant asymptote. It's going to look like this. These are going to be pretty interesting also. Okay, so I'll show you. F G F prime G prime x squared plus 4 2x 2 2x. So we got 2x times 2x minus 2 times x squared plus 4. 4x squared minus 2x squared minus 8. Four minus 2 is 2x squared minus 8. X squared minus 4 over 2x squared. Set that equal to 0. Is x equals plus or minus 2. Those are my vertices. So when f equals -2, we got -2 squared plus 4. 2 times -2, so it's 4 plus 4. -4 equals -2. F of +2 is 2 squared plus 4, 2 times 2. 4 plus 4 over 4. So we have -2, -2, and 2, 2. The vertices. And the second derivative of that function. X squared minus 4, 2x squared. 2x, 4x. 2x squared squared. 2x times 2x squared minus 4x x squared minus 4. 4x cubed minus 4x cubed plus 16x. 4x to the 4. So we have 16x, 4x to the 4, 4 over x cubed. So no point of inflection because the top cannot equal 0. But we have a vertex at 2 and -2. That is because the graph is going to look like this. It's symmetric about that line. So the graph looks like this. That's what the graph looks like. Okay, it will take practice. I mean, watching me do it is one thing, but I strongly suggest is after class today, look at those again. Example. F of x equals e to the power 2 over x. So u is 2 over x, which is 2x to the power -1. So du is -2x to the power -2. The first derivative is eu du, which is -2 over x squared. -2e to the 2 over x squared. That's my first derivative. So there are no vertices because you can't make the top equal 0. The second derivative, -2e to the 2 over x squared. -2e to x squared. So the derivative of e to the 2 over x is e to the 2 over x times -2 over x. It's the same as the top one. So we have x squared times e to the 2 over x times -2 over x squared minus 2x -2 e to the 2 over x. So x squares cancel here, so we just have e to the 2 over x minus 2 times -2. X squares cancel. Negative and negative makes it a positive. 4x e to the 2 over x to the 4th. E to the 2 over x, -2 plus 4x. So the point of inflection is where -2 plus 4x equals 0. So it occurs at e to the 2 over 1/2 makes it e to the 4th. 2 times, flip the bottom, 2 over 1 makes it e to the 4th. So, right, 1/2 e to the 4th. That's the point of inflection. Now I got to put all this stuff together. We know we have no vertices. So what does the graph look like? We have e to the 2x. What does that graph look like? We know what e to the x looks like. It's an exponential function. We know what e to the power 1 over x looks like. It's a decreasing function. So it's e to the 1 over x squared. So it's going to be a faster decreasing function. No, what is, hold it, hold it. This can't be right, hold it. Because x cannot be 0. Basically what this thing's saying is the x root of b squared. So yeah, so if it's a fraction. As x goes to 0. As x goes to 0. That's for positive x's. For positive x's, the closer x gets to 0, but negative, it's a decreasing function. Negative. We have a vertical asymptote at 0 and a horizontal asymptote at 0. So that makes it -2. E to the -1, 1 over e. So 2. Next is -1. E to -2. Okay, so my first derivative says no vertices. Check, there's no vertices. And the second derivative, the point of inflection is at 1/2. This one's gonna be. This one looks like. E to the power 2 over x. No, that's not right. E to the power 2 divided by x. No. E to the power 2. All that to the power 1 over x. No. Stupid calculators. All right, so we know what e to the x looks like. E to the 1 over x. vertical asymptote there. And the horizontal is the x-axis. So there has to be a point of inflection as 1/2. And x cannot be 0. I have to come back on that. But that the derivatives are correct. Last one. Get you guys out of here before midnight. Cosine x. This one looks horrible. Oop. This one looks horrible, but isn't that bad really. What? Let's look at the derivatives. What's the first derivative going to be? No. Minus. Because that's the coefficient. The derivative of x is 1. And the second derivative of negative sign, that goes to 0. So extrema, we set negative sine x minus square root of 2/2, set that equal to 0. And then the point of inflection, set negative cosine of x equal to 0. And we know that. So change the signs, cosine x is 0 at pi/2 and 3 pi/2. Negative sine x equals square root of 2/2. Move that one over there. Change the signs. So we have sine x equals negative radical 2/2. Where is sine x equal radical 2/2? It's when they're both the same. Sine and cosine are both square root of 2/2 at the same place. 45-degree angle, which is take 180 divided by 4. Or pi divided by 4. By 4. So it equals negative square root of 2. So where does it equal negative square root of 2/2? Because square root of 2/2 is positive here, negative here, positive here, and negative here. But we only want it in this domain. Oh, it's 2 pi. So we want it at x equals pi/4 to 3 pi/4. 5, 6, and then that's 7 pi/4. Those are where our vertices equal negative square root of 2/2. No, sine is negative. It's going to be at these two places. It's at 5 pi/4. Yeah, negative square root 2/2 for sine is negative in the third and fourth quadrant. Sine is positive in the first two quadrants, negative in the second. So it's 5 pi over 4 and 7 pi over 4. And then cosine of x, the point of inflection is at pi over 2 and there. Okay. Now it wants me to graph this. Okay. So this is the function we're going to graph. Oh, no more paper. No. It's almost 2 o'clock already, guys. Now, there are a couple of them I want to finish. I want to work on it and see if I get the right answer. I get to see the graph of it. I know this one looks like that. Anybody put a calculator?
So like, it would look like this, right?
That-
Was it wrong?
Yes, that's exactly what it's going to look like. That makes sense because this whole side here, when it have x 2 over x, when we have 2 over x, it's a decreasing function on the negative side. Very good, thank you. Yeah, because we know that e cannot be negative. This side here, when x is positive, it's a decreasing function. It's just that when x is negative, we have 2 over negative number, which it has to be increasing as it gets negative. Thank you. That's the part I was missing. Okay, so we'll pick up from here tomorrow. Actually, I'll pick up from here and show you what the last one should look like and the one that was skipped earlier. Then